Okay. So, position time graph, you have three options. One of those is right, A, B, or C. So, A is the top one, B is the middle, C is the lower lip curve. So how many have A? Okay,
I have A.
everybody has A.
Yes, that's it.
Why can't it be B? What would B indicate?
It's constant. It's wrong.
What's wrong, okay? What would be, why is B wrong?
Because velocity was changing.
Yes. So B would mean that it would start, it would go away at a constant velocity, and then it would come back at a constant velocity, okay? That's what B would represent. B is correct because it does show a direction change, okay? But it shows that there's a constant velocity going and a constant velocity coming back. What would C indicate the cart was doing? Does C show a direction change?
Yes.
That part's right. But if you look at the beginning, what's the cart doing as it's going away from me? If C was right, what would the
Speeding
cart
up.
be doing?
It's accelerating.
Speeding up.
Speeding up, okay?
Accelerating.
Well, both A and C show it accelerating,
Oh,
okay? So C would be the cool one to watch because I would push it and it would start off slow, and then the farther it got away from me, the faster it would go. And then it would start back really fast, and then it would slow down right before it got to my hand. Okay? That would be cool to watch. So you go whoop, like this. Okay? And it would slow down right before it got to me. So they do have in common that the fact that they all show a direction change. But A is right because A shows it. This is the classic example of a direction change. It slows down. At the top, you can draw a tangent line that has a slope of 0, indicating that the velocity is 0. And then the slope changes line, those tangent lines become negative, and it begins to speed up. Now, what does somebody have for their velocity time graph? Vanessa, what do you have for the velocity time graph?
Kind of like the opposite
A
of
V.
the other one, but it's like pointy.
Like that,
Yeah.
kinda? Like a V?
Yeah.
Okay. Elliot,
That, but it's not a V, the line just continues slanting down.
Yeah,
That's what I
past
had,
past
so I
0.
had-
Yeah.
so you have,
Zero guy racing. Can we copy off?
something like that. Those are the only two options that we have.
There's probably
I mean,
more
it
out
starts.
There's-
I mean, you could probably draw a circle or something too.
Oh, I could,
Yeah.
but that's not.
there. Thought a circle was wrong.
So one of those is right, okay? One of those is right. Now, let's start with this. Start with what you saw happening. Did you see the cart change direction? Absolutely. Okay, the cart changed direction. So what three things has to happen for the cart to change direction? Slow down,
Stop.
speed back up. Do both graphs show it stopping, slowing down, stopping, and speeding back up?
Yes.
Absolutely they do.
Oh my gosh.
They both show it slowing down, stopping, and speeding back up. Because both lines are approaching 0. Now, Vanessa, let's talk about your graph. Did the cart change direction?
Yeah.
What has to happen to the sign of velocity if it changes direction? Switches. So if I saw your graph, this is what I would think the cart did. I would think I pushed it and it rolled away and it slowed down and it stopped. But on her graph, what would the cart do?
Keep going on.
It would start speeding up going in the same direction. Because your graph never crosses through 0, 0 to show a change in direction. Okay? So that's why that line that slopes through there is correct. So here's another way that you can represent this, okay? And oddly enough, it boils down to F equals ma again. When I let go of it, what was the only force acting on the cart?
Fan.
The fan, okay? There was gravity in the floor itself, but we'll deal with those later. The main thing affecting the motion was the fan. So, and this is a handy thing to get into the habit of doing, is thinking this through in terms of vectors. So here is the cart, I pushed it. It had a certain initial velocity, okay, we're gonna call that V1. Then, when I draw V2, one of three things could happen. Either V2 is getting bigger, V2 is getting smaller, or you're at a constant velocity and V2 is gonna stay the same. As soon as I let go of it, what did the cart begin to do?
Slow down.
Slow down. So that means when I draw V2, I'm gonna draw V2 a little bit smaller, and then I can draw V3. So it's still going in this direction. Velocity is a vector quantity, it has magnitude and it has direction. But those vectors are getting smaller in this direction, okay? So, is it accelerating? Because my velocity vectors are changing. So once you know it's accelerating, either the acceleration vectors point in the same direction or they point in opposite directions. Dylan, in which direction do you think the acceleration vectors are going to point? Same direction, opposite direction?
Same,
Nope,
opposite.
because it's slowing down, right? So if you're defining this direction as being positive, that means that it's going to have some negative acceleration, okay? This is why this graph initially has that negative sloping line, because force equals mass times acceleration. Mass is a scalar quantity. Mass can never be negative. So force and acceleration always have to have the same sign. So if you have negative force, you have to have negative acceleration. So when that car was going away, the velocity vectors were getting smaller because you had a negative force creating a negative acceleration. That isn't the tough part, okay? Conceptually, you all are cool with that. That's in your wheelhouse. Great, working at positive velocity, negative acceleration. I get it, cool, okay? The tricky part comes when it begins to roll back. You all intuitively have a bias that says, oh, my acceleration should change sign as well. My acceleration should be positive. But it doesn't, because it's the same negative force creating the same negative acceleration. Now, here's the cool thing when it starts to roll back. When this thing starts to roll back, okay? Go on. Now, I'm going to have a negative V1, I'm going to have a negative V2, I'm going to have a negative V3. So on the way back, notice my velocity vectors are now pointing in the opposite direction, and they're getting bigger. So when something speeds up, what do you know about the sign of velocity and acceleration?
It's the same.
Same sign. So on the way back, I still have the exact same negative acceleration vectors. So I have the same acceleration vectors on the way out as I do on the way in. And they're the same because I have the same negative force acting on the same mass, creating the same negative acceleration, which is why this is a straight sloping line, because that shows the same acceleration the entire time, because I have the same force acting on the cart. Okay? Makes sense. Okay, so stop that camera for a second. Dylan, I apologize.